Welcome back to the deep dive. Today we're really going to dive into, well, probably the most fundamental question in AI.
And it's a tricky one, maybe even a messy one.
Oh, definitely messy. How do we actually measure intelligence in these AI systems we're building?
Yeah, it's a huge challenge.
Because, you see the headlines, right? AI achieves superhuman performance. It beats us at Go, complex video games, generates amazing text.
The spectacle is incredible, absolutely.
But then you try to take that same system, nudge it just a tiny bit outside its comfort zone, its training data.
And it often just falls apart.
Exactly. Brittle, needs so much data, can't really make sense of things if they're slightly different from the billions of examples it's already seen.
That brittleness, that lack of real understanding or adaptation, that's the wall we keep hitting. It's holding back the promise of, more general AI.
It really is. And it feels like the core problem is, well, we don't even agree on what we're aiming for.
That's it. For decades, the field's kind of been split.
Yeah.
Two different ideas about what intelligence is.
Okay, what are they?
Well, one view, you could think of Minsky and others early on, saw intelligence as basically a big bag of tricks, a collection of specific skills. Can it do task X, task Y, task Z?
Right, like a checklist of abilities.
Exactly. But the other vision, going back to Turing, McCarthy, they saw intelligence as something more fundamental, a general learning ability.
The ability to figure things out, to adapt.
Precisely. Can it get good at new problems efficiently? And, well, because it's easier to measure, easier to put on a chart.
We defaulted to measuring the skills. We celebrate the score, the win in the game.
And that's why the way we often measure progress is, frankly, broken, or at least incomplete.
Okay.
So our mission today in this deep dive is to unpack why just looking at skill is misleading. Then we want to introduce a newer, more formal idea, intelligence as efficiency.
Efficiency, interesting.
And finally, show you a benchmark, the abstraction and reasoning corpus, or ARC, that's actually designed to measure that efficiency.
All right, let's do it. Part one then. Why the skill metric fails us. You mentioned the history. Early AI just wanted machines to do things that looked intelligent if a human did them.
Yeah, that was the initial goal. Seems reasonable, right? If a human needs intelligence for chess, let's build a chess machine.
But that led to this AI effect.
Exactly. It's this weird paradox. Jose Hernandez-Araujo pointed it out really clearly. AI has gotten incredibly good at doing tasks without actually being intelligent in the general sense.
How does that work?
It's like the magic trick effect. As soon as we figure out how the machine does the task, how the algorithm works, it stops feeling intelligent to us.
Right, we see the gears turning.
We mistake the artifact, the result, like the chess move, for the process of intelligence that produced it. A human wins at chess, we think, wow, smart. Deep Blue wins.
We think, wow, fast computer, clever programming.
Exactly. We don't credit it with general intelligence.
Okay, but hold on. If Deep Blue plays chess better than any human ever, isn't that intelligence? I mean, performance in the real world. Isn't that what matters? Isn't the score the point?
That's the million-dollar question, and it gets right to the heart of the confusion. The performance, the score, it only matters as evidence of intelligence if it reflects an efficient learning process.
Okay.
And what we found is engineers can basically buy that amazing performance in two main ways, and neither way really tells you much about general learning ability.
Okay, what's the first way to buy performance?
Unlimited prior knowledge. Think Deep Blue again.
Right, the chess machine.
Incredible engineering, no doubt. But it wasn't really learning chess in a general way. It was packed full of human chess knowledge. Specific algorithms like Minimax, huge databases of openings, endgame tables, all hard-coded by the developers.
So that was like a hyper-specialized calculator for chess moves.
Pretty much. It was built to solve one problem. It shocked everyone when it beat Kasparov. But researchers quickly realized it didn't teach us much about how we learn or think. It was an artifact, a brilliant one, but not general intelligence.
Okay, that makes sense. So less about learning, more about expert knowledge being poured in. What's the second way?
The modern way. Unlimited training data.
Big data.
Massive data. Look at OpenAI's AI that played the video game Dota 2, called 5, to get it to a world-beating level.
How much data did it need?
The equivalent of 45,000 years of gameplay.
45,000 years, wow.
Astronomical. And even then, it was still brittle. Its skill was bought with sheer brute force experience, not necessarily clever adaptation.
So it wasn't efficient learning.
Not really. And guess what? Even though it could beat the pros, regular non-champion human players found ways to beat its restricted version by using weird, unexpected strategies it just hadn't seen enough of in those millennia of training.
Huh. So even 45,000 years wasn't enough to cover all the bases if it wasn't truly generalizing.
Exactly. It shows a limitation.
Okay, so the big takeaway here seems to be, if intelligence is really about the process of learning efficiently, of acquiring skills efficiently, then just looking at the final score, the superhuman performance, that's missing the point.
You've got it. Achieving skill at task X doesn't really show intelligence unless maybe task X is itself a meta task, like being good at learning lots of different skills quickly.
We need to look at the resources it took, the prior knowledge, the amount of practice, the data to get that score.
That's the crucial shift in perspective.
All right, so if the score is misleading, we need a different measure. You're saying that measure needs to focus on generalization.
Yes. We have to get rigorous about what generalization means. Simply put, it's the ability to handle situations or tasks that are different from what you've encountered before.
Different how? Are there levels of difference?
Absolutely. It's not black and white. It's really a spectrum. We need to break down generalization because dealing with a slightly blurry cat picture is very different from, say, figuring out quantum physics.
Okay, lay out this spectrum for us. What's at the basic end?
At the low end, you have what we can call local generalization or maybe robustness. This is where most current deep learning models excel.
Like the image classifier.
Right. It sees a new photo of a cat, maybe from a weird angle or in bad lighting, but it still knows it's a cat. It's handling new inputs, but they come from the same basic kind of data, the same known distribution it was trained on. It's robust to variations within a single known task.
Okay, makes sense. What's the next step up?
That's where we get to broad generalization, or flexibility. This is much harder. It's about handling a whole category of related tasks or environments, including situations the creators maybe didn't even think of, dealing with unknown unknowns within a domain.
Can you give an example?
Sure. Think about a truly self-driving car, like level 5 autonomy. It needs to handle any road situation, any weather, any weird thing another driver does safely. Or Steve Wozniak's famous coffee test for a robot.
The coffee test.
Yeah. Could a robot walk into any random person's kitchen, find the coffee, find a mug, figure out the unfamiliar coffee machine, and actually make you a cup of coffee? That requires flexibility across a huge range of potential problems.
Wow, okay, that's a big jump from recognizing cats. And what's at the very top end?
That's extreme generalization or generality. This is the ability to handle completely new types of tasks, maybe ones that only share really abstract similarities with anything seen before.
Like human fluid intelligence.
Exactly like fluid intelligence. The ability to look at a totally novel puzzle, like maybe one of those Raven's matrices tests, and just figure out the underlying abstract rule, even if you've never seen shapes or patterns like that before. Right now, only biological systems really demonstrate this.
And this connects to how we think about human intelligence.
It mirrors it very closely.
Yeah.
In psychometrics, the study of human intelligence, you have things like the CHC theory, a hierarchical model, and right at the top sits the G factor general intelligence. Yeah, and that G factor lines up almost perfectly with this idea of extreme generalization or fluid intelligence. So the goal for AI, if we want general AI, should be to measure these broad adaptive abilities, not just the narrow skills they might produce in one specific context.
Okay, so we need to measure the ability to generalize, ideally across that whole spectrum.
Yeah.
This leads us to your proposed new framework. Intelligence isn't just skill, it's skill acquisition efficiency.
That's the core idea. Let's try to define it formally. The intelligence of a system is, essentially, a measure of how efficiently it acquires new skills across a relevant range or scope of tasks.
Scope is important here. It's not about being universally intelligent.
Yeah, no, and that's a key point. Human intelligence isn't universal either. Think about physical fitness. Humans evolved bodies optimized for, say, persistence hunting on the savannah, but that underlying adaptability lets us learn to do things far outside that context, like climbing Mount Everest or playing basketball. Our intellect is similar. It's incredibly broad, but it's still specialized, probably shaped by evolution for certain kinds of reasoning, social interaction, tool use.
So for AI, we shouldn't aim for some mythical universal intelligence, but maybe focus on developing a specifically human-like kind of intelligence.
Yeah.
Efficient within that human-relevant scope.
That's the argument. Let's build AI that learns and adapts efficiently in the ways that are characteristic of human cognition.
Okay, if we're defining intelligence as efficiency, like a conversion rate, turning resources into skill, we need to know what those resources are, what needs to go into the equation, what variables matter.
Right. To measure efficiency fairly, we have to account for the inputs. There are three crucial ones we need to consider, conceptually at least.
What's the first one?
First, the priors. P. This is basically all the relevant knowledge or structure the system starts with.
Like the hard-coded chess rules in Deep Blue.
Exactly. Or maybe a huge language model it was pre-trained on. Or even the fundamental architecture of the network. The more help it gets upfront via priors.
The less impressive its learning efficiency is because it didn't have to figure that stuff out itself.
Precisely. It got a massive head start.
Okay, priors. What's number two?
Second is experience E. This is the data, the practice, the interaction with the environment it gets during the learning process.
Like the 45,000 years of Dota playing.
Exactly. But crucially, when we measure this, we should really focus on the novel, informative experience. We shouldn't give as much credit for just grinding the same stuff over and over. More data isn't always better learning.
Right, diminishing returns on just raw data quantity. Priors, experience. What's the third variable?
This one is maybe the most important for measuring true generalization. Generalization difficulty.
Okay, generalization difficulty.
Yeah.
How do we measure how hard it is to generalize for a specific task? That sounds complicated.
Conceptually, it comes from ideas in algorithmic information theory, but we don't need to get lost in the math. Think of it intuitively.
Okay, give me the intuition.
GD is high for a task if the simplest, most obvious pattern or strategy that works during the training phase fails spectacularly and has to be fundamentally rethought for the test phase.
Okay. An example.
Imagine training an AI on tasks where the goal is always pick the biggest blue shape. It learns that simple rule easily, but then the test task is suddenly find the object that's symmetrical.
The old rule is useless. Worse than useless, it's misleading.
Totally useless. The AI has to discard the simple biggest blue heuristic and figure out a completely different, more abstract concept symmetry. The edit distance between the simple training solution and the necessary test solution is large. That means high GD.
I get it. IGD means you can't just memorize or find a simple shortcut based on the training examples. You have to understand a deeper, more abstract principle to succeed on the unseen test cases.
That's the essence of it. It forces abstraction and adaptation.
So priors, what you start with, experience, what you gather, and generalization difficulty, how much you need to adapt. How do these fit together to define intelligence conceptually?
You can think of intelligence as the rate at which a system converts its priors P and its experience E into skill, especially on tasks with high generalization difficulty, GD.
So a highly intelligent system is one that needs very little P and E to solve tasks with very high GD.
Exactly. It's informationally efficient, it learns quickly and adapts flexibly, even when the rules change significantly. It's not about the final score achieved at any cost. It's about achieving skill cost-effectively in terms of knowledge and data, particularly on challenging novel problems.
Okay, that theoretical framework makes sense, but how do you actually test that? How do you build a benchmark that forces this kind of efficient generalization?
That brings us to the practical application. The Abstraction and Reasoning Corpus, or ARC.
ARC, tell us about it. What makes it different?
ARC was designed by François Chollet precisely to measure this kind of efficient, human-like fluid intelligence. It looks a bit like those Raven's progressive matrices test visual puzzles where you have to figure out the abstract pattern.
Okay, visual grids and patterns. But lots of AI benchmarks use images. What's special here?
The design constraints. They are laser-focused on forcing what Chollet calls developer-aware generalization.
Meaning the AI system has to generalize, not the developer finding tricks.
Exactly. First, it uses few-shot learning. Drastically few. On average, an AI only sees about 3 demonstration examples for each task.
3 examples, that's it.
That's it. So you absolutely cannot rely on massive data sets. Brute forcing with data is impossible.
Okay, that tackles the unlimited experience problem. What else?
Second, the tasks in the hidden test set are guaranteed to be novel. The developer cannot have trained their AI on tasks that use the same core logic. The AI has to generate the solution, essentially write a mini program to solve the task's logic on the fly, based only on those 3 examples.
It has to infer the underlying abstract rule from almost nothing.
Precisely. And third, and this is crucial, ARC is very explicit about the priors it assumes the test taker should have. This allows for a fairer comparison between humans and machines.
Controlling for the P variable, the starting knowledge. What priors does ARC assume? You mentioned these connect to human cognition, the core knowledge priors.
That's right. These are based on developmental psychology research, looking at the intuitive concepts that seem to be innate or develop very early in human infants across cultures. They are the building blocks. ARC assumes the solver brings these to the table.
Okay, what are these 4 core knowledge areas?
Number 1 is objectness and elementary physics. The basic idea that the visual scene can be broken down into distinct objects that stick together, move as units, persist over time, and interact through contact, like a block pushes another block.
Makes sense. Objects.
Yeah.
What's 2?
Number 2, agentness and goal-directedness. The intuition that some changes might be caused by an agent acting intentionally to achieve a goal rather than just passive physical reactions. Recognizing purpose.
Okay. Agency. 3.
Number 3, natural numbers and elementary arithmetic. Basic number sense, counting small quantities, comparing more or less, maybe simple addition or subtraction. Crucially, this is usually limited to small numbers, like under 10, reflecting human cognitive limits.
Got it. Basic numbers. And the last one.
Number 4, elementary geometry and topology. Recognizing things like straight lines, symmetry, rotation, grids, containment, what's inside what, connectedness, abstract spatial relationships.
Like seeing a pattern needs to be completed symmetrically, regardless of the specific shapes or colors used.
Exactly. It's about those abstract properties. ARC tasks are designed so that you likely need to combine insights from several of these core knowledge domains to figure out the rule.
So what do the tasks actually look like?
They are grids. Input grids and output grids, fairly small, maybe up to 30 by 30 squares, using only 10 different colors or symbols. You see a few cares showing the input to output transformation. Then you're given new input grids, and you have to construct the entire correct output grid from scratch.
And scoring.
It's binary. You either get the output exactly right for all the test inputs for that task, or you get 0, no partial credit.
Tough. So what's the big implication of ARC? How well do current AI systems do?
Well, humans find ARC tasks solvable, often quite quickly, leveraging those core priors. But current state-of-the-art deep learning methods, they perform very poorly, often close to 0.
Really? Why?
Because ARC deliberately avoids relying on learned knowledge about the real-world language, specific objects like cats or cars. It's pure abstract reasoning from minimal data. Deep learning models excel at pattern recognition in massive data sets, but they struggle fundamentally with this kind of few-shot abstract rule inference and program synthesis. They can't efficiently use those core priors, or they lack them entirely.
So ARC is essentially a test designed to bypass the ways current AI buys performance, massive data, and specific learned knowledge, and directly measure that fluid, adaptive, efficient generalization ability based on core intuitive priors.
That's the goal. It's a benchmark for fluid intelligence, for skill acquisition efficiency.
This really feels like a potential paradigm shift then, moving away from celebrating the spectacle-beating Go champions acing video games towards a much more rigorous measurement of the underlying process.
Yes, focusing on the efficiency.
Yeah.
How effectively does a system turn limited information, low P and E, into the ability to solve genuinely novel problems, high GD?
It's less about the height of the jump and more about how little runway you needed.
Beautifully put. ARC is one concrete attempt to enforce that. But the philosophy is broader. We could, for instance, repurpose existing benchmarks. Instead of just measuring the final skill level in Dode 2, measure how much less data the next version needs to learn a different but related strategy game. Or introduce teacher-student setups, where one AI constantly generates novel, challenging tasks to push another AI to keep learning and adapting, forcing open-ended development.
Measuring the learning rate on novel challenges.
That's the future direction. Continuous, efficient adaptation, not just static performance on a fixed benchmark.
This changes the game for AI development. Less about hitting a score, more about building systems that genuinely learn and generalize efficiently. Okay, to wrap up, let's leave our listeners with something to chew on.
That's good.
If intelligence, this human-like general intelligence we're aiming for, is really about the efficiency of turning limited information and basic priors into skill at truly novel problems. Think about your own job, your own expertise.
Yeah, consider this. How much of what you do relies on vast amounts of specific knowledge you've acquired over years versus how much relies on those fundamental core knowledge priors, objectness, agency, numbers, geometry?
And linked to that, how quickly could you master a completely new abstract task If all you had to go on were those four basic intuitions and just a couple examples, it really makes you think about the nature of intelligence itself.